Welcome to Early Experiments to Characterize the Atom. So this is all about models of the atom and developing our model of the atom beyond what Dalton introduces us to. So Democritus, remember, said that matter is made up of indivisible particles called atoms. Now he doesn't really say anything more than that. He doesn't give us a picture, an image of what an atom looks like. But I tend to think that Democritus thought of it something like bricks in a wall. He thought that as you get closer and closer to looking at a wall, instead of just seeing one big giant mass, he thought, well, just like a wall is made up of bricks, stuff must be made up of atoms. Something indivisible. Now, okay, we know that we can break bricks apart into half bricks, crumbs, but let's pretend that they can't. Right? So he's assuming that atoms can't be divided any farther. You can get down to just a single atom, but he's not really saying anything about the structure of what's inside the atom. And that sort of makes sense because he has no idea. He just thinks that you can't break them apart anymore. So now we get to Dalton, and Dalton also thinks that atoms are indivisible. And so he's coming up with this idea of basically a billiard ball kind of thing. It's just a ball of stuff. And you can't split it apart. So he says that atoms combine in certain ratios to form compounds, and that means that we must have one particle of this atom and one particle of a different element that combine together, and they must be indivisible in some way. Well, they're different from each other. So remember that Dalton is working in the early 1800s, and so for roughly 100 years, there's not a whole lot of development as far as structure of the atom. So, in 1903, J.J. Thompson comes along and he studies electrical discharges in a partially evacuated cathode ray tube. So, an old television, before we had flat screens like this one, had cathode ray tubes in them. So if you ask your parents, grandparents, great-grandparents maybe, they may tell you that the cathode ray tubes of their day, the televisions were very large, they were deep, because there needed to be space for these cathode rays. Now, cathode rays now we know are just electrons. But at the time, Thomson didn't know what they were. He just knew they were cathode rays. And they were called cathode rays because they came off of a cathode. The cathode was positively charged, and so they were attracted to the cathode, which is positively charged. So these are streams of negatively charged particles. These were electrons, although he didn't know that they were electrons at the time. So he's got a metal electrode, and he's got another metal electrode. If he puts a voltage difference between them, one is negatively charged, one is positively charged, and in between it's mostly evacuated glass, so it's mostly vacuum. There's a little bit of gas inside. And so what he noticed was that the cathode ray, so that's sort of this green bit here, was repelled by a negatively charged plate. So if he put two plates on either side of the stream as it moves to the right here, so the stream is moving that direction. If he puts a negative charge here, well, the stream gets repelled away from the negative charge. And if he puts a positive charge there, the stream gets attracted towards that positive charge. So what this means, because we know that like charges repel each other, and opposite charges attract, just like the poles of a magnet. If you put a north pole and a north pole of a magnet, they'll repel each other. If you put a negative charge and a negative charge next to each other, they'll repel each other. So he was able to say, well, this means that these cathode rays must contain negatively charged particles, and then we go on to call them electrons. And Thomson reasoned that since the electrons could be produced from various types of metals, that means that all of these metals, and probably all atoms, even nonmetals, must contain these electrons, these negatively charged particles. But that means that if all atoms contain negatively charged particles, then the atom must not be indivisible. We must be able to get these electrons out. Which means that now, finally we have an image of an atom that isn't just a sphere that is all one solid bit. now we have some negatively charged electrons, so those are these yellow dots here with a negative charge, inside the atom, and as far as Thomson knew, the rest of the atom was just a diffuse positive charge. And so this leads to his model of the atom that he called the plum pudding model. So in England at the time, plum pudding was, plums were raisins, so it was basically a raisin pudding kind of thing. It was a little bit like a fruitcake kind of thing, where you've got these, you've got the pudding, which is a positive charge, and that's sort of a diffuse positive charge, and then you've got these little denser islands of negative charge in there, and we can get those out of the atom. And so we've got these localized electrons in a positively charged cloud, and something like raisins suspended in pudding. Now, I like to call this, instead of plum pudding, because I've never eaten plum pudding, but I have eaten chocolate chip cookies. So I call Thompson's model the chocolate chip cookie model, where we have the dough, which is sort of this red positively charged bit, and then we have the chocolate chips, which are the negatively charged electrons. So note now that atoms are not indivisible anymore, since they contain smaller particles. They all contain electrons, at least. And so now atoms are no longer indivisible. So now we know that that portion of Dalton's theory is wrong. The rest of it still holds up, though. So we're starting to get structure within the atom, inside the atom. So let's go a little bit farther. So in 1911, Ernest Rutherford performs an experiment, his famous gold foil experiment. So he takes a thin gold foil and he hangs it there. And into this thin gold foil, he shoots, from this direction, he's shooting some positively charged alpha particles. Now we know that alpha particles are the nucleus of a helium atom. So it's 2 protons and 2 neutrons, so it has a charge of 2+. But all he knows is that they're positively charged, and so he's shooting these positively charged particles this way at this thin gold foil. Right? It's very thin, and so what he expects to happen is that basically he's got a bunch of things like this. This is Thomson's model of the atom, where we have our diffuse positive charge. The positive charge here is the blue cloud, and then we've got little bits, these electrons that are in there. And so if this is true, what do we expect? Well, we're throwing in these positive charges, and we expect most of them, once they enter this cloud of positive charge, the positive charge is all around, which means it's being repelled equally from all directions. So they're going to pass through this positive cloud largely unchanged. And the only real difference is if we pass through only at the edge, or if we get very close to one of the electrons. Right? So maybe we'll come out with a slight angle here, but most of them will go straight through with just a little bit of spreading. Right? That's what he expected. Now, that is not, in fact, what he saw. So, if Thompson's model is right, if the chocolate chip cookie model or the plum pudding model is correct, then the alpha particles should only be deflected just a little bit. But instead, most particles are passing straight through, but some of the particles were deflected at very, very high angles. He didn't expect very large angles at all. He expected just a small deflection. But in order to get really, really high angles of deflection, some of them, in fact, came back. So if you look back at our example here, he expects most of the particles to go through and end up over there. And just a little bit of deflection on some of them. So he expects a few over here and a few over there. But he finds some that are really highly deflected, and some that, in fact, hit the foil and then come back towards him and hit on this side of the foil. Which shouldn't happen if Thompson's model is right. There's just no way that can happen. And so these highly scattered particles have to have encountered something with a very large positive charge and a relatively high mass. Because again, if you have something with a relatively low mass coming in and striking something else with a relatively low mass, like if we have an alpha particle hitting an alpha particle, we expect that second alpha particle, the one that's being collided with, to be moving at a fairly high speed afterwards. Right? Like if I take two ping pong balls and one of them is still and I throw one in, well, I expect that second ping pong ball, the one that's being hit, I expect that second ping pong ball to be bouncing pretty far, pretty fast after the collision. But what he's basically finding is that, well, he's getting the ping pong ball to come in, and most of the time it's just sailing through and not hitting anything. But every once in a while, it hits something and it's coming back. It's coming back at it, which means that it's encountering something that is very, very heavy and also has a very, very high positive charge. Because if it doesn't have a positive charge, if it's neutrally charged, well then it's not going to influence the positive charge. So he's got something that is very, very dense, very, very heavy, very, very small, because most of the alpha particles are going through. So this now, he later claimed about this experiment, he said, "It was the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell, an artillery shell, at a piece of tissue paper and it came back and hit you." Now, of course, if you fire a bullet or an artillery shell at a piece of tissue paper, you expect it to go through. Right? And that's what he was expecting. But to have it come back at him was really, really surprising. And the only way that if I fire a gun, if I fire a bullet at a piece of tissue paper, if that bullet comes back at me, that means that that bullet had to have encountered something really, really dense. And so the same thing is true for these alpha particles. The alpha particles have to be hitting something that's very, very dense, which means that now Rutherford has to introduce the idea that Thompson's model is not fully correct, that we may have these electrons scattered throughout, but also we have to have something in there that now we call the nucleus. That nucleus has a very high positive charge and it's very heavy. It has a lot of mass to it. So, again, Rutherford could only explain his results using a nuclear atom. The atom has a very dense, positively charged nucleus at its center. Now, it doesn't have to be at the center based on his experiment, but that's where it is. And he's saying that electrons are moving around the nucleus at distances that are very large relative to the size of the nucleus. The nucleus has to be very small compared to the size of the atom because almost all of the particles are going straight through. It was only about 1 in 8 or 10,000 particles that got deflected at all. So later experiments show that the nucleus contains positively charged protons and neutrally charged neutrons. And the electrons are then outside. So now, using Rutherford's nuclear model, now we have a model of the atom that contains both electrons and a positively charged nucleus. Now, with Rutherford, we don't yet know that there are protons and neutrons involved, and we still don't know what the electrons are doing or where exactly they are. We just know they're outside, kind of moving around somewhere, doing something. And we still don't know yet what's inside the nucleus. Now, of course, modern times, now we know that there are protons and neutrons in there, but just with Rutherford's experiment, we don't know what's inside the nucleus. So that's where we were after early experiments to characterize the atom.